Hello, welcome to today's video. Today we're picking up where we left off from in the previous further maths tutorial video where we were looking at Argand diagrams and loci, but today we're going to take it up a notch by basically showing how we can end up shading entire regions on the graph if inequalities are involved in the loci. So, the best way to show this stuff is just to jump straight into examples, to be honest. But when I'm saying that, I would point out to you, I'd recommend that you go back, if you haven't already, and watch the video on loci, on Argand diagrams that I did previously, because a lot of the understanding behind why the things that we're doing today end up being the way they are comes from a lot of the things and details that we went through in that last video. So, for this first one, we know straight away this is going to be related to a circle because it's a modulus on one side, a number on the other. We know the center of the circle because it's take away this complex number, then it's the complex number you can see as it is. So it's positive 1, positive 3i, but that is only because it's a minus with the brackets in front of that entire complex number. We also know, because there's the 2 on the other side, this is related to a radius of 2. So therefore, we end up drawing a circle with center 1, 3. So marking that on our diagram like so. And then because it's a radius of 2, we know it's not going to quite make it to the real axis, but it is definitely going to be big enough of a radius to cross the imaginary axis. So therefore, drawing that on, terrible circle drawing incoming. There you go. I promised bad. It's not too bad, but still, it's not great, is it? But it'll do. That will get me all the marks. Almost. Almost, because the next thing we've got to do is now, because there's an inequality sign now involved, unlike the last video, we end up having to shade a region on this Argand diagram. Now, the region you shade makes complete sense when you realize what is going on, because if it's equal to 2, we said last time, and as we've already drawn, that is a circle with radius of 2. If you're saying less than, then that means we're saying the radius could be less than 2. And if you for instance, drew that, well, let's say, for instance, you had a radius of 1. 1 is less than 2, so that works. And that would be just a circle with the same center, but a smaller radius. So a circle that's smaller inside our previous circle. Now, the thing is, though, we're not saying less than 2, but only whole numbers. It's every single number in the world less than 2, real numbers. So therefore, that would end up meaning you're basically drawing an infinite number of circles, all with smaller radiuses, or radii, I should say, than the radius of 2 that we already had. And that would end up effectively, eventually being indistinguishable from just shading all of the region inside the circle. So that's what we do if it's a less than or equal to. We just basically end up shading everywhere inside the circle. Now, worth pointing out to remind you, don't need to shade in by colouring in. Obviously, you're welcome to if you want, but to save time, you're welcome to just do a load of lines, basically some sort of indication that you know is shading inside the circle. So that's clear from my diagram, and we're done with the first example. On to example 2, where now we're going to look at, oh my goodness, what happens if it's a greater than? So, first of all, again, linking to previous stuff, we know it's going to be a centre. That's a terrible E. A center of positive 2 minus 6i, again because it's minus in the brackets. We know it's related to a radius of 5, but watch out, this time it's not including the 5 because it's not greater or equal to 5, it's just greater than. So therefore we are going to say, okay, there's 2, we're going to say, okay, there is, let's say, minus 6. And then we're going to draw the circle, but instead of drawing with a solid line, we're going to do a dotted line, because it doesn't include the equals. So there we go, a bit of notes to add. Cool, right then, so therefore doing that as a dotted line, we'll have something that looks like this as a circle. Again, dreadful circle. It's vaguely circular, it will do. But this time, also because it's greater, instead of looking at smaller circles, we're looking at bigger circles. So that means instead of shading inside the region, we're going to be shading outside the region. So we're going to be shading everywhere out here. That's got a lot of shading to do. You can hear that from probably the sounds being picked up on the microphone as I shade on my tablet. There you go. Be careful not to shade inside the circle. So necessarily, be a bit more careful when shading around the area of the circle. He says immediately then shading inside the circle. There you go. Do classic teacher thing of do as I say, not as I do. And there we go. That would be the answer for this one. Everywhere except for inside the circle. Nice. On to the next example, and we're now going to be looking at the loci that involve arg notation. And we remember, hopefully from the last video, these end up being half lines. Half lines that start at the point that, again, is written inside the algebra, inside the brackets. Watch out, though, for, if the number is also in some additional brackets with a minus in front. If it's not, you have to reverse the number you see. So, therefore, this time that's not the case. So, therefore, we have to realize instead of positive 4, which is written inside, it's secretly negative 4. And instead of negative I, it's secretly positive I. So, our line is going to be starting at negative 4, positive 1. So, over there, let's say. Labeling our axes again. Okay, so we might remember from last time that if we're dealing with arg of z plus 4 minus I is equal to pi over 6, that would be a line with an angle of pi over 6 in comparison to the positive real axis. But because we're not starting on the real axis, therefore we kind of have to do sometimes a dotted line to give us a reference point. So therefore, from there, because it's a positive argument, that would be anti-clockwise measure from this horizontal line. So therefore, we're going to end up with a line that looks something like this. And there we go, that's pi over 6 as an angle. Right, okay, so that's the first bit done. But then we also have the inequality on the other side, and that's equal to, including the equal of 3 pi over 4. Again, if either of these were just a less than or a greater than, then you wouldn't do a solid line, you'd do a dotted line for these things. But anyway, they're both inclusive, so I'm going to draw a solid line. 3 pi over 4 would be all the way around here. Terrible straight line. Please use a ruler. Again, I'm being a hypocrite. Don't hate me. So there we go. A straight line, inverted commas, over there at an angle of 3 pi over 4 from a simulated real axis. Cool. So that's if you're doing just the two boundaries. But again, of course, we've got an inequality. So what we want is all the things in between there. And if we're thinking about all the angles in between 3 pi over 4 and pi over 6, well, that would result in us shading this region here. So in between our two lines, but be careful, think carefully about what direction the inequality signs are going in and whether we're going to be anti-clockwise or clockwise and all that sort of stuff. So the reason I'm shading in between here rather than all the way around here is because it's between 3 pi over 4 and pi over 6, and as you increase arguments you go anti-clockwise. So that's why we started at pi over 6 and went anti-clockwise to the 3 pi over 4, because that's what happens when you make angles bigger on an Argand diagram. You go anti-clockwise. Anyway, getting rid of that other line just to make it clear that's not what I was okay. So there we go. That bit was just, pardon me, sort of emphasizing something. Cool. So that is the loci. Brilliant. On to the next one, and we're going to be going on to the perpendicular bisector style ones. Of course, again, you see the number that's here, and if it's not in its own brackets with a minus in front of it, then you've got to do the minusing yourself by realizing it's the opposite of what you see. So instead of plus 1, it's minus 1. Instead of minus 2i, it's positive 2i. So that'll be the point. Let's say minus 1, positive 2. Let's say that's about there. And then instead of minus 1, well, then it's positive 1. So therefore, on positive 1 on the real axis, because of course if it's just 1, no imaginary number there, it's only a real number, so only on the real axis. And we know from last video it's perpendicular bisect. Now, because our 2 points conveniently are a gradient of minus 1 in relation to each other, we can see that because we've gone 2 to the right when we've gone 2 down. Therefore, as a result, we know our perpendicular bisect will have a nice perfect gradient of 1. And also we know the midpoint's a nice place because it's on the imaginary axis, so therefore we also will know our imaginary axis intercept. So putting that all together, we will have a line that looks something like this. There you go. Did a bit better without the ruler this time. Still not perfect. Use a ruler. But there you go. So that is a rough idea of what the line looks like. This time I've marked on the intercepts. Remember, as I said in the last video, if it's a particularly nice gradient with a particularly nice midpoint that allows you to just instantly be able to know where those intercepts and stuff are, then do it. If not, don't unless they ask. Always read the question and check whether they, what information they do or don't want marked on the diagram. Now, last time I did say something you can do is you can indicate with a dotted line and as a right angle sign which side of the, not which side, the fact that the line is perpendicular to the line joining our 2 points. So you're still welcome to do that, but once again, really extra important you do a dotted line to make it clear it's not part of the shaded region. Anyway, I did a solid line because, again, we've got an inequality that's inclusive. It's got the equals included. But to know which side of the line to shade, or where to shade, I should say, in a full stop, it all goes back to understanding why this type of loci looked like a perpendicular bisector in the first place. So, a reminder that it all comes from the fact that this left-hand side means the distance, because of the modulus, and it's the distance from the complex number that we did the dot for before, so from -1 plus 2i, to the point z. And the points z are meant to be representing the points we are shading. And then this notation on the right-hand side is saying the distance from 1, positive 1, to, again, the point z. And the point z are the ones we're going to be indicating in the diagram, the ones we're going to be shading. So therefore, if we're saying these points, which are the distance from -1 to the points we're -1 plus 2i to the point z that we're shading, is got to be a greater or equal distance from the distance from 1 to z, that means we're saying we want our point z to be further away from -1 plus 2i than they are from 1, because it's a greater distance between z and -1 plus 2i than it is from 1 to z. So therefore, if we want it to be a greater distance from -1 to 2i, that's going to be this side of the line, because we know all the points on this side of the line are going to be nearer to 1. So therefore, they are further away by logic, further away from -1 plus 2i. Sorry, difficult to talk while shading at the same time. So there we go, some dreadful shading, but that's enough shading to give the idea that's the side of the line to draw on. So this is these loci in particular that it's really important you understand why that notation is the way it is. I have some students try and remember tricks about why they shade one region rather than the other. So they, some tricks like involving like all the inequality signs pointing to the -1. So that's the side you shade and things like that. But the problem with those sort of tricks is those are the sort of tricks then very easy to forget because you can't remember why we do that. So that's why I'd recommend understanding the logic behind the notation, because if you understand that, then it's more clear why we do shade a particular side. Okay, on to the final bit, which in reality is just bringing together all the things we've done before. What they can do is they can, do things as you can see in the example we've got here, where first of all, people freak out because it looks quite complicated. Worth pointing out, this is just set notation. And then the other thing is we've got more than one loci written here, and then also crucially there is the intersection symbol. Now it's worth pointing out another way they sometimes word this is instead of having the set notation with the intersection symbol, they might just write the two loci, region, algebra things, and just write the word "and" in between them. And that means the same thing. And mathematically, in terms of logic, is the same logical argument as what the intersection symbol is saying. So, therefore, putting that all into practice, think about each loci individually. So, for instance, this first one is going to be a circle with a center of -3, -3. So let's say that's about there. -3, -3. It's including the radius of 7. So therefore radius 7, let's say that's a circle that looks something, let's say like this. Dreadful circle, as always. There you go, look at that, nice and wobbly. Brilliant, it'll do though. So there we go, that's our circle. And normally we would be shading everywhere inside that circle. It's less than or equal to 7. But, hold fire, because we've also got to do the other argument and, well, it's an argument, but I mean the other loci. And we've got to see where we're going to be shading with that loci as well before we do any shading, because we only want to shade the region that works for both. Where do the two regions overlap, intersect, whatever you want to call it. So for the other one, it's arg of z, which means luckily this time it's starting at 0, because it's like secretly it's got z minus 0 written inside the brackets. Obviously, we don't bother writing z minus 0, it's redundant, but that's what it's saying. So our line is starting at 0, and we're going from 2 pi, minus pi over 2, sorry, which is effectively the imaginary axis, all the way over to 2 pi over 7, which is, I don't know, something very vaguely, roughly, let's say this. So that's 2 pi over 7. Of course, pi over 2 minus pi over 2 is all the way down there, so going downwards. And therefore, we're looking in between there. That would normally be all of this region. I'm going to erase it in a sec, but all of this region here shaded. That's what it would normally be for the argument bit. But, as I said, we're not going to shade that region at the moment because we want the region that's shaded for both. So, if we're thinking about that, we want what's the region that's shaded for the arg bit. As we said, that's in between the negative imaginary axis and the line that I marked at 2 pi over 7. And then the circle one was everything inside the circle. So therefore, the region that's inside both, where the two regions overlap, in other words, will just be this region here. So it's inside the circle, but still in between our two lines caused by the arg loci. So there you go. That's the region we end up shading for that particular example. Lovely. Nice. So that's the answer to that question. Just think about what the two individual loci will look like, and then, you know, do draw the lines on where they've got to be, but then the only region you end up shading is the region that satisfies both. Nice. One final example, and you're probably looking at this going, wait a minute, what's changed? Aren't you cheating? Isn't this just the exact same question? And I go, oh, it's very similar, but there's just one change, and that is that there is now a union symbol. Now, it's worth pointing out, I can't recall if they've actually ever done this yet in an exam question, but I'm just trying to, you know, predict the future. And, you know, there's no reason why wouldn't they? What if we can do intersection, why can't we do union? And it ultimately is a case of just understanding what this means from maths A level, which is basically you've got to treat these like two separate mini questions. Do this loci, shade it. Do this loci, shade it. Union is just anywhere that's been shaded at the end of that. So the union is really quite nice because it means you don't have to be worrying about what works for both. You can just treat them like their own mini questions that you're just doing on the same diagram. So therefore, once again, minus 3 is the center of a circle, radius is 7, so something that looks like this. Terrible circle for a second time. And then for the other one, well, no, I finished that one off. So therefore, that would be if it's less than or equal 7, everywhere inside the circle for 7. There you go. And then that's that one done. Now moving on to the other one, 2 pi over 7. We said was that line there roughly. So that's 2 pi over 7. Pi over 2 was of the negative imaginary axis again. And again, we can just consider this loci separately and just shade what works for this loci. So therefore, that is everywhere in between our two straight lines. So that is all of this region here. And again, I'm not worried about where's been shaded twice. Where works for both of them, it's union. So just anywhere that's shaded is the answer. So that's why I'm just shading all of this stuff. Cool. There you go. Last thing I guess I could point out is they do, you know, could involve, as I said in the last video, doing things such as im of z is greater than or equal to, I don't know, 6. If you got that sort of situation, of course, just realize from the last video, im of z is a horizontal line, re of z is going to be a vertical line if you get one of those like that. So if you get something like, I don't know, minus 9, that would be a vertical line, and then you're obviously shading depending on what direction along the axis you're going in. So those are other ones you could get. Brilliant. So that concludes this video. So hopefully you found that useful. We're going to have one more video on Argand diagrams for core pure content, and we will be basically looking at how you can do more advanced stuff on Loci, on Argand diagrams, so stuff that involves a bit of problem solving, all that sort of stuff. So look out for that video particularly if you're aiming for an A star and A, because those are the sort of questions, that push you a bit more rather than just remembering off by heart like we are with, to a certain extent, a lot of the skills we looked at so far. Nice. Have a good time.